Hello friends, I welcome you in lecture number 16 on series solutions of differential equations. In previous lecture, we have discussed about Bessel's equation and we have seen that particular solutions of Bessel's equation are known as Bessel's function, and we have written the formula for Bessel's function of the first kind of order nu. We recall that formula for Bessel's function of order nu. It is denoted by j nu x and it is given by x to the power nu sigma m equal to 0 to infinity minus 1 to the power m x to the power 2m 2 to the power 2m plus nu times m factorial. This is into m factorial and gamma nu plus m plus 1. This is Bessel's function of the first kind of order nu, where nu is a non-negative real number, and we have seen in lecture number 15 that this j nu x is a particular solution of Bessel's equation of order nu. Now this Bessel's function is a special type of function. It is known as special function, and we have assumed here that this nu is a non-negative real number. Now we are going to discuss one question on the Bessel's function of first kind of order nu. Here nu is a non-negative real number, so for different values of nu we will have different Bessel's function of that particular order. For example, I can take nu equal to 0, then I will have Bessel's function of order 0. I can have nu equal to 1 by 2, that will give me Bessel's function of order 1 by 2. I can have nu equal to 3 by 2 also, that will be a Bessel's function of order 3 by 2. So today we are going to derive the formula for Bessel's function of order 1 by 2. We will take nu equal to 1 by 2 in this formula, and we will see that this Bessel's function of order 1 by 2 is nothing but multiple of sine function, trigonometric functions sin x. So we are going to derive that formula for Bessel's function. They can ask you to write down the Bessel's function of order 1 by 2, and they can ask you to prove that formula in terms of sine function. Sometimes instead of this symbol nu, they are using different symbols. They are using small p to denote Bessel's function of order p. So in that case p is a non-negative real number. So these different notations we must be familiar with. Some authors are using j nu x to denote Bessel's function of order nu. Some are using j suffix px to denote Bessel's function of order p. So whatever notation is used in the question, we will use that notation. So this type of question was asked in GTU Summer 2019 exam, where they have asked to write down the Bessel's function jpx of the first kind of order p, and using that formula we have to prove that Bessel's function of order 1 by 2 turns out to be a multiple of sin x, and multiple is square root of 2 over pi x. First we will write down Bessel's function of order p, and for that we will simply replace this symbol nu in this formula which we have derived in previous lecture, and we will be able to write down Bessel's function of order p. So first I am writing that part of the question. We have to write down the Bessel's function of first kind of order p. Bessel's function of the first kind of order p is given by the formula j suffix px we had used nu. In that formula we had written x raised to nu. Instead of nu I am writing small p. Sigma m equal to 0 to infinity, and here in the numerator minus 1 to the power m x to the power 2m. Here we have 2 to the power 2m plus nu. Instead of nu I am writing small p into m factorial into gamma nu plus m plus 1. Instead of nu we are writing small p, that is gamma p plus m plus 1. This is Bessel's function of the first kind of order p, where p is a non-negative real number. This is first part of the question. Write Bessel's function jpx of the first kind of order p, and hence show that j1 by 2x is given by square root of 2 over pi x into sin x. So to derive this formula, we take p equal to 1 by 2 in this formula, and we try to derive that formula for Bessel's function of order 1/2. So taking small p equal to 1 by 2, we get, so now we are writing j suffix 1 by 2 function of x. We have x raised to p, that is x raised to 1/2. Sigma m equal to 0 to infinity minus 1 to the power m x to the power 2m 2 to the power 2m plus p. Instead of p I am writing 1 by 2 into m factorial into gamma p plus m plus 1, that is gamma 1 by 2 plus m plus 1. Here I have taken p equal to 1 by 2 here and here. Rest of the things as it is. Now we try to simplify this series. This square root of x I can write in this way also. Here this I can split as 2 raised to 2m into 2 raised to 1 by 2, and that I can take outside summation. This I am writing as 2 raised to 2m into 2 raised to 1 by 2. This is independent of m, so I can take it outside summation, and sigma m equal to 0 to infinity minus 1 to the power m x to the power 2m. Here we are left with 2 to the power 2m m factorial. Here I can combine 1 by 2 and 1, that is 1 by 2 plus 1 is 3 by 2 plus m equal to 0 to infinity. This again I can rewrite as square root of x divided by square root of 2, and now I can expand this summation. I can write down few of the terms corresponding to different values of m, and I will try to prove whether I obtain the series of sin x multiplied with this factor. If you recall from the mathematics 1 course, we know that Maclaurin series of sin x is x minus x cube by 3 factorial plus x raised to 5 by 5 factorial minus and so on, alternately positive and negative, and here we have only odd powers of x. So we will try to prove that j1 by 2x turns out to be this series of sin x multiplied by square root of 2 over pi x. So for that we try to write down few values of this sum corresponding to different values of m. For m equal to 0, I will have minus 1 raised to 0, that is 1, x raised to 0, that is also 1, 2 raised to 0, that is 1, 0 factorial is also 1, and gamma 3 by 2 plus 0, that is gamma 3 by 2. So corresponding to m equal to 0, we have only gamma 1 by 2. Now I take m equal to 1. So for m equal to 1, this is minus 1 raised to 1, that is minus 1. So we will have negative sign, and if I take m equal to 1, here we have x raised to 2 into 1, that is x square. If I take m equal to 1, here I have 2 raised to 2, this is 1 factorial and this is nothing but gamma 3 by 2 plus 1. Now I am taking m equal to 2. So for m equal to 2 we have minus 1 raised to 2, that is 1. That means we have positive sign, and here I will have for m equal to 2 this is going to be x to the power 4. For m equal to 2 here we will have 2 raised to 4 into 2 factorial into gamma 3 by 2 plus 2, and so on. We are writing for m equal to 0, 1 and 2 only, and let's try to simplify further. Now in the next step, if you observe, we want to prove that this is equal to multiple of series of sin x, and here we have odd powers of x, and here you can see we have even powers of x. So for that I have to multiply every term of this series by x, so that I can adjust. I divide by x and I multiply by x, this quantity as it is. Now I am multiplying every term by x, and therefore to set that multiplication by x I have to divide by x. So I am considering 1 by x into x, and this x I am multiplying with each term of this series. So let me write x in the denominator here, and here every term will be multiplied by x, and this gamma 3 by 2 I can rewrite as gamma 1 by 2 plus 1, and I have to take care that I multiply by x every term. So I have x cube here. Here I will have 2 raised to 2, that is 4. 1 factorial is 1, and using the property of gamma function, gamma 3 by 2 plus 1 is 3 by 2 times gamma 3 by 2 plus, here also I have to multiply by x, so I will have x raised to 5. 2 raised to 4 is 16 into 2, and gamma 3 by 2 plus 2, that we can rewrite as 3 by 2 plus 1 plus 1, and next term will be negative. Now in the next step I am simplifying all these things, and for that let me write one more step. Here I can see that I have square root of x, and in the denominator I have x. That x I can write as square root of x. So that square root of x will get cancelled, and here we will have square root of 2 into square root of x, and gamma 1 by 2 plus 1 is 1 by 2 times gamma 1 by 2. We are using this property frequently. Gamma n plus 1 is n gamma n, minus, let's see what we obtain here. Here this 2 will get cancelled, and here I will have 3 into 2, and gamma 3 by 2 again I can rewrite as gamma 1 by 2 plus 1 plus x raised to 5, this 16 into 2, that is 32, and this becomes 3 by 2 plus 1 is 5 by 2 plus 1, and so on. Let's further simplify this. This I can rewrite as square root of 2 into x. Here I have gamma 1 by 2 divided by 1 by 2. So this 1 by 2 I can take in the numerator. 1 over 1 by 2 is 2, and gamma 1 by 2 is square root of pi minus x cube divided by 3 into 2 into gamma 1 by 2 is 1 by 2 into gamma 1 by 2 plus, this is x raised to 5, 3 by 2, gamma 5 by 2 plus 1 is 5 by 2 times gamma 5 by 2, and so on. So again we simplify. We have 1 over square root of 2x. Here I have 2x divided by square root of pi minus This 1 by 2 I can take in the numerator, so I have 2x cube divided by 3 into 2 into gamma 1 by 2, that is square root of pi. And I can consider this cancellation of 32 divided by 2, that is 16 into 5. Here I have x raised to 5, and let me simplify gamma 5 by 2. Here we are simplifying gamma 5 by 2. Gamma 5 by 2 we can rewrite as gamma 3 by 2 plus 1, and this is 3 by 2 into gamma 3 by 2. Again gamma 3 by 2 can be written as gamma 1 by 2 plus 1. So again I can use that property, gamma n plus 1 is n plus 1 gamma n, and this is 3 by 4 into gamma 1 by 2 is square root of pi. So that I can directly substitute here into 3 by 4 square root of pi and so on. Now if you observe, in the numerator we have square root of pi in every term. So let me take that pi, square root of pi common. So I have square root of 2x into square root of pi, and here I am left with 2x minus 2x cube divided by this I can rewrite as 3 into 2 into 1 plus you can see here I can consider this cancellation, x raised to 5 and 4 will get cancelled, and we have 5, 4, 3 and 2. 5 as it is, this 4 I will obtain from here, 5, 4 and 3, and 2 is not there. It is square root of pi minus and so on. And now let me rewrite this again, square root of 2x into square root of pi. Here I have 2x minus 2x cube divided by 3 into 2 into 1. Now here if I want to use the formula of n factorial, I must have 5, 4, 3, 2 and 1, but 2 is not there. That I can set here. I multiply and divide by 2 in this term. So I will have 5, 4, 3, 2 and 1 and so on. And now we have 2 in the product in every term, so I am taking 2 outside, and here I again rewrite this as square root of 2 into square root of x into square root of pi. I have taken 2 common, so here I am left with x. In the numerator I am left with x cube, and this 3 to 1 is nothing but 3 factorial, plus in the numerator I have taken 2 common. This 1, 2, 3, 4, 5 is nothing but 5 factorial, and this will continue the pattern in a similar way. And 2 over root 2 is square root of 2 divided by this I can combine these two as square root of pi into x, and this is nothing but Maclaurin series of trigonometric function sin x, and this is again rewritten as square root of 2 over pi x into sin x. Therefore we have shown that Bessel's function of order 1 by 2 is nothing but square root of 2 over pi x into sin x. So here we have used properties of gamma function, and we are using just the definition of Bessel's function of the first kind of order p, and we are interested in the Bessel's function of order 1 by 2. So we have taken p equal to 1 by 2, and then we have written few terms corresponding to m equal to 0, and from this we are able to generalize that this is nothing but Maclaurin series of sin x. Therefore j1 by 2x is equal to square root of 2 over pi x into sin x. So in this way you can write down the formula for Bessel's function of first kind of any order. You can try by taking p equal to 3 by 2 in that formula, and you will obtain the formula for Bessel's function of order 3 by 2. Similarly, you can write Bessel's function of order 0, Bessel's function of order 1, and so on. So this is very interesting question, and here we are just rewriting and rearranging the terms of this summation so that we are able to obtain the Maclaurin series of sin x, and we are able to derive this formula for Bessel's function of order 1 by 2. So this is all about this session. I hope you like it. Thanks for